Hi, the last couple of lessons have been quite theoretical, so in this one we're going to apply some of that knowledge, and we're going to render some particles to go with our falling chunks of rubble. Here's a particle sim I've set up, which will represent gritty, sandy material falling together with the rubble pieces. This is actually a PBD, point-based dynamics, or grain sim, just so that we get the pieces building up a little amongst the rubble. Here's how it looks from a wide view. And here's the closer view we were rendering in the last lesson. As you can see, these particles have the standard grain solver sprites assigned, so they look like little balls. This isn't super realistic, so we're going to come up with something a bit better. The first thing we'll do is remove the sprite attributes and any other attributes we don't need. It's very important, particularly when we're rendering lots of points, to delete any and all unneeded attributes and groups, because these can greatly increase the size of the cache and slow down caching and rendering as all that data gets written to and read back off the disk. You should always think carefully about whether you really need an attribute before you write it into a cache. Let's drop down a group delete. And I'll just expand our spreadsheet here. So we have a lot of attributes. We have a few groups. So I'm going to get rid of our groups, and then I'll get rid of some attributes. Now sometimes it's easier just to delete all of the attributes and then keep a few. We probably want to keep velocity and ID. We'll need ID. Shouldn't be any vertex attributes because these are particles, and there's one primitive attribute which we don't need. We can delete all of the detail attributes. They don't take up much space, but we may as well be tidy about things. Okay, so now we have no sprites because we've killed all the attributes that were associating the sprites with our particles, but everything should be a lot lighter. We can check this by looking at the info pane. So it was 128 megabytes, and if we look at it now, it's 27 megabytes. So we've reduced the amount of memory that's taking up quite considerably. That's, about a quarter of what it was. So that's pretty good. However, we are going to add some of that back. The next thing we're going to need is something to instance to our particles. So I'm going to do what I often do with this and start off with the box. And we'll append an ISO offset, and we'll append to that a scatter, and I'll just reduce that down to 25. Then we'll shatter a box with a Voronoi fracture, plugging in our scatter. I'll just turn off the template flags on those. Okay, so now we have a shattered up box. We like all of these pieces to be centered on the origin, so there are a bunch of ways of doing this, but a quick way to do it would be to append and assemble SOP, and we will create pack geometry, and then we'll append an attribute wrangle, and we'll just set p equals 0 on all of those. And what that's done is each of these now just is associated with a single point rather than a point at each corner of the box or each corner of the fractured piece. And this has just snapped all of those pieces to the origin. So these are all now neatly on the origin. So I'm just going to unpack these because I actually don't want them to be packed anymore. And I will transfer the name attribute back onto our unpacked pieces. So if I look at the info on this, we now have polygons rather than pack geometry as we had before. The next thing we're going to need is a way to isolate single pieces of this collection of objects. And one way to do that is to take our name attribute. I'm going to remove that prefix. So now the name is just 0 to 24. So that's our 25 pieces. And we can have a blast and we're going to make name equal $F minus 1000, and I think we'll need to wrap that in some backticks so it gets evaluated properly. Okay, so what this is doing is it's looking at our name attribute and it's taking the current frame, it's subtracting 1000 because our timeline is starting at 1001. So if the current frame is 1012, it's giving us a number of 12 and it's comparing that to the name attribute. And it's blasting everything else because I have delete non-selected on. Okay, so I'm going to call that blast by frame. And we'll cache that out. We'll call this instance pieces. And we'll cache that from 1001 to 1025. Actually, let's cache it from 1000 to 1024 because that will line up properly. Okay, and if we load this back in, we should get the same geometry. So in our load from file settings, we're going to change this from all geometry to packed disk primitive. And we'll just set that to display as full geometry so that we can actually see what we've got. Okay, and that's looking great. Now that we have packed disk primitives being read off disk, let's copy stamp them onto our points. So we'll put down a copy to points and we'll connect in our pieces, we'll connect in our points and then see what that looks like. Okay, I can see a couple of problems. The first problem we have is that our pieces are very big, so let's make them a little bit smaller. Now we could have done this before we cached them, but it actually makes a lot of sense to have this afterwards because it makes it very easy to tweak the look of the sim. Okay, that's looking a bit better. Now, another problem is that they're all the same piece and they're all oriented the same way. So let's fix the orientation first. So this time we'll go over to this side of our network and we'll append another attribute wrangle. We'll pop that in there and I'm just going to paste this in for speed rather than typing it. And this is going to set a random orientation for us. So we have a seed value here. And what's going on inside the wrangle node is that we're taking a seed and then we're using that seed to generate a random vector called u. And then we're using this very handy function called sample orientation uniform, which will give us a uniform quaternion orientation if it's given a 3-digit vector, 3-digit random vector. So we're putting our random vector in here and it's returning a quaternion, a 4-digit vector, which we're calling orient. And copy to points knows how to use that orient attribute to, let me just show that. There it is. There's our random orient. And copy to points knows how to use that in order to make all of our pieces point different directions. Right, the next thing we'll do is randomize the pieces of geometry that are being instanced to our points. So we'll do this by dropping down another attribute wrangle node. Oh, I'm sorry, that should actually go after our copy to points. And again, I'll just copy paste the code in, and then I'll talk through what it does. So we'll create the parameters for this with the handy button. And we're going to set this to start at 1000 and end at 1024, because those are the frames that we cached our geometry pieces out to. And now we've got different pieces of geometry on each point. Right, so going through the code, the first thing we're doing is we're getting the file name. So prim intrinsic is grabbing that file name. Then I'm splitting that into pieces based on the period character. Which we're using to separate different parts of the file name. And then I'm taking the point number, which is associated with this primitive. So this point number integer contains the point number of the point associated with this particular pack prim. It's very simple with pack prims. There's a one-to-one mapping. So each point will have one primitive associated with it, and it will have the same number. Then I'm using this expression. I'm fitting a random value based on the point number, and I'm just expanding that range out to go from 1000 to 1024, our start frame and our end frame. And then I'm just converting that from an integer into a string so that we can put it into our file name. Then I have a loop here where I'm rebuilding the file name based on, it's all exactly the same except that I'm swapping in that number where appropriate. And then finally, I'm setting the unexpanded file name intrinsic to our new file name. Now that we have that working, I'm just going to shrink the parameters window down a little bit, and I think we can probably reduce the size slightly. And if we look through our simulation camera, we can start just tweaking things so that everything renders nicely. I'm going to cache this out on quarter frames using the same kind of expression setup that we had before. I'll come back when this is finished caching and we'll do some test renders. Now that we've cached out our particles, let's read them back in. I want to read them in as a pack sequence primitive, which the file cache node doesn't support. So I'm going to drop down a vanilla file node, and I'm going to copy the geometry file path, and I'm going to paste that into the file node as a relative reference. And then we want to set this to packDisSequence. I'll keep it displayed as bounding box, and then we need to remember to set the frame range. So I'm going to use the RF start and the RF end expressions for that. And then we'll make a null, which we'll name out, so that we have somewhere to grab the output of this network. We're back at the object level, and it's time to create a render object for our particles. Let's call that render particles. We'll turn off the display flag and we'll just sit it underneath the others. And if we go inside, we can jump down and object merge node. And we'll point that at our particle sims out and hit accept. And we'll pop down a null and we'll call that render. And we'll set the display flag there. We're also going to need a material node. And we will need to create a material. I'm actually going to base the shader for our particles on the shader I created for our rubble pieces. So let's take a look at that. If we go to render view and RBDs and hit render. Okay, now that that's rendered, we can see that we've got this sort of, muddy concrete kind of look to this with a few pebbles sticking out of it. These are some scan textures. So they're reasonably close to how these actually looked. And I think that what I would like to do for the particles is to use the same shader, use one of these shaders, and then just randomly choose the point on the shader to evaluate for each particle. They're so small that I don't think we need to see variation across the surface of the particles, but we'd like to get some nice variation on the particles as a whole. We'll grab one of these shaders, we'll duplicate it, and we'll figure out a way to modify it so that we can just grab a random point. I'm going to jump into the MatNet, and let's just take the first of these. These are all essentially the same shader, they just have different maps plugged into them. So I'll duplicate that, and I'm going to call this particle shader. And we can see that it has some various controls for diffuse, roughness, displacement, reflectivity, and so on. I'm going to go in, and the first thing I'm going to do is look at everything that's contributing to displacement and remove it, because I don't think that we want displacement on our points. This stuff is all displacement. That's going into the displacement. So is all that. And all of this. I think we can get rid of that and not touch anything else. And that as well. Okay, so we dramatically simplified this shader. Now looking at this, the thing that tells this shader where to shade what color and what texture is this UV parameter. So what we're going to do is replace this with a reference to something that's unique on the particles. In order to do that, because the particles are packed geometry, we're going to need something called a render state VOP. We'll put that down, and we're going to be looking for the particle ID. So let's change that to integer values, and we will type packed and ID. And this should allow us to grab the ID attribute from the particles. So we'll take that and we'll plug that into a rand function. And what we want from this is ideally to replace a UV, we're going to want a vector attribute. So let's output a 3D vector. So this is now giving us a random 3D vector for every point. And we should just be able to plug all of these guys in here. Delete the UV parameter. And with a bit of luck, this should work. So we'll go back up. And we'll jump into our render particles node, and we'll just point this material node at our particle shader. And we'll see how that renders. Just double checking that the ROP already points at render particles. So we'll just choose that here and press render. While we're waiting, I'll just point out that this is set to 6x6 pixel samples, and we have 5 time samples for transform and geo. We probably don't need the time samples for the transforms because the camera's not moving and nothing else at the object level is moving, but it doesn't really take any extra power to render that. And in the geometry tab, we're set to 8 sequence segments. Okay, we're starting to see something. There's a fair amount of motion blur geometry here, so it's not going to be terribly fast on my 12-core machine. Okay, that render is finished, and I think it looks pretty good. So the next thing we'll do is render a ROP that has the ground and also the pieces of rubble in as well. That will be this one. I'll just do a test render of that. Okay, I'm pretty happy with that. So we'll kick off a render of the whole frame range and we'll see how it looks moving. Here's our render of the particles together with the rigid bodies. There are definitely things that we can improve here. I think the scale of the particles could be a little larger to ensure that we have good contact with the ground plane and the rubble. The sim could also use a little bit of turbulence to break up these very linear trajectories that the particles have as they fall. However, the actual rendered look, I think, is good. The shading and the motion blur matches the rubble pieces really well, and we have some very natural looking color variation between the different grains, which I think is quite successful. In this lesson, we learned how to instance simple packed disk primitives to particles and how to modify an existing shader to match other scene geometry. I hope this has been useful, and I will see you in the next lesson.